This morning we've got two talks before the coffee. The first one's going to be Kenta Hotokezaka from Princeton, and he's going to talk about macronova R-process elements in neutron star mergers.
Thank you very much.
There you go. Very good.
Thank you very much for coming here. So today I want to focus on the macronova emission and neutron star mergers, more like theory side. So here's my outline. So I will introduce some important concept of neutron star mergers. Actually, majority of this Masaru already talked about it yesterday, and I will focus on macronova, kilonova, and I will also talk about synchrotron radio and X-ray flares arising from fast tail of the merger, and then our process budget in the universe. So next to my talks, Tsubi will talk about jet stuff. So I will not really discuss about the jet, but Tsubi will do it. So let me introduce this. So neutron star mergers are interesting because of the target of the gravitational waves and the possible progenitors of short gamma ray burst and possible origin of the R-process elements. So I think I don't need to give a detailed introduction. So let's start. So this is a brief summary what we expect after the merger. So two neutron star merge. Then depending on the total mass of the binary, we expect different scenario. So if the total mass is sufficiently small, we expect stable rotationally supported supermassive neutron stars formed. But if the mass is sufficiently heavy, then outcome is just immediately black hole formation and maybe the disk. And there is also intermediate case, the hypermassive neutron star formed, and then probably the lifetime is 10 milliseconds, maybe up to 1 second, depends on the mass and equation state. And afterward, it collapses the black hole and forms a torus. So I want to emphasize that there are some variations in neutron star mergers depending on the mass. And here is some result from neutron star merger simulations. So this is phase space, shows the total mass of the binary system from 2.6 solar mass to 2.9 solar mass and the different equation state. And here I show here this equation state has smallest radius and this one has a sort of large radius. And you can see, and these equation state can support the maximum mass larger than 2 solar mass. So here you can see some massive merger result. The outcome is immediate formation of the black hole, but here you can see sometime supermassive black hole. Supermassive neutron stars formed. And important result from LIGO's event here is the mass is around here, and also up around 2.7, between 2.7 and 2.8. And also there is some constraint from tidal deformation, tidal deformability parameters, and we can, there is some constraint on the radius of the neutron star. So basically, for this event specifically, we expect something like maybe hypermassive neutron star, maybe a black hole is formed. And if we have, in the future, we have, for example, small mass neutron star merger, we expect something like maybe supermassive neutron star is formed after the merger. So then we expect some sort of different kind of EM counterpart we expect. So, and after the merger, there is some mass ejection that Masaru yesterday showed. This is equatorial plane. You see some material is ejected after the merger, and this arrow is about 0.5 C, and the fastest one travel like 0.8 C. And typically, the velocity is 0.1 to 0.3 C. And the morphology is something like this. This is equatorial plane, and this is XZ plane. There is some material ejected even at the pole. This has important implication to the jet and the ejector interaction, which results in cocoon. And another mechanism of the mass ejection is a disk wind. So after the merger, we have a black hole torus system or neutron star torus system, which also ejects some material. So this is one of the simulations. And this is some estimate of the dynamical ejector mass and disk outflow taking from different simulations, from different groups. And here just they take like 10% of the accretion mass is just ejected by the disk outflow. So then you can see here this phase space at most like 0.1 solar mass is ejected, and like least case is 10 to the minus 3 solar mass. And both can be comparable, or disk outflow can dominate over the dynamical mass ejection. And typical velocity of this disk outflow component is usually we say it's 0.05 c, which is correspond to the alpha recombination energy, because nucleon just recombine to the alpha particles and then release 5 MeV, and then what typically you get is this sort of velocity scale. So, and then based on these outflows, people try to model the macronova, kilonova observed in this GW event. And important thing, I want to introduce this R process abundance. This is solar R process abundance as a function of the atomic mass number of each element. So here there are 3 peaks, and first peak, second peak, third peak, and people often talk about this lanthanoid. So lanthanoid is between the second and third peak here. And the important thing is most of the mass, if you say from first peak to third peak, then most of the mass is around first peak, about 90 to 80% of the mass. And sometimes we call this is light R process element, and this around here to up to uranium we call heavy R process element. And maybe if you're from outside of this field, perhaps you wonder why we keep talking about the red component, the blue component, and why it's two colors or something like this. So basically from the simulation, so far we understand, for example, dynamical ejection and black hole disk wind. So neutron richness is sufficiently high, and usually what we get is a robust R process element, I mean heavy R process elements. For example, these calculations shows the robust production of the beyond second peak, for example, the second peak and third peak, but not much around the first peak. So usually dynamical ejecta and this black hole disk wind, we expect sort of heavy R process element. So this is before the discovery, we think this is sort of the robust composition of this merge outflow. And also there is some idea about if you have neutron star and which lives long enough, then neutron star emit strong neutrinos, and then composition changes. So for example, this calculation shows, for example, so this is different cases for which neutron star lifetime is different after the merger. For example, this one, this gold color, you see huge amount of elements around the first peak, but not much element around the lanthanoid elements. So in this case, what you expect is very small fraction of lanthanoid, and in the end, what you get is lanthanoid, more or less lanthanoid-free outflow. And in fact, if you calculate radiative transfer calculation, depending on the lanthanoid fraction, what you get is different light curve. Here, for example, this is completely lanthanoid-free case. This is just iron opacity. Then lanthanoid fraction is 0. Then what you have is peaking around at less than 1 day and then decline. And if you include solar lanthanoid fraction, let's say lanthanoid fraction is about 3% in the mass, then what you get is this faint and longer peak, and then opacity is 100 times higher than this case. And of course, you have like 0.1% of the lanthanoid, what you get is something in between. So it depends on the lanthanoid fraction, you have different kind of signal. So this is so important. And so this is some evolution of kilonova model from Brian's paper. So initially, Lee Paczynski proposed this idea and fixed the Brian and Roberts et al. Fixed the heating rate, and the luminosity drops. And then afterward, we calculated this the opacity based on this abundance pattern. Then what we get is red and slow macronova. But then people come up this scenario that the lantern is free outflow, then it's blue. So sort of this, so theorists think this way. So maybe in this outflow, the emission is redder, and this outflow, the emission is bluer. So in this sense, we have this terminology, red and blue kilonova. So let me summarize. So two neutron stars merge, and depends on the mass, you have different outcomes. And the dynamical ejecta usually not so large. What we see is usually up to 0.02 solar mass, and likely a little bit less than 10 to the minus 2 solar mass for the dynamical ejecta. And this queen, the velocity is slower, but can be the mass is more than the dynamical ejecta. And the composition is also different. For example, this case may be composed by heavy element, and in this case, maybe some neutrino irradiation. We expect some light and heavy element. And in this case, we expect strong neutrino irradiation, so more light elements are expected to form. So this is a summary of this outcome. So, and then I want to move on to macronova and kilonova studies. So this is a brief summary of what is macronova or kilonova. It's same things, but the name is some people call different name. And this is, roughly speaking, just thermal photons generated by radioactive decay inside the ejecta, and these photons diffuse out from this expanding ejecta. It's quite similar to supernova emission. So the luminosity is something like this. So the radioactive power is continuously declines with time, but the photon, what you see, is rise and decline, because at first time the photons cannot diffuse out from the system, so the initial radioactive power just wasted by the adiabatic expansion. So we don't see much photons. But here the photon diffusion times is around 1 dynamical time, then photon can diffuse out. So after this time, the luminosity follows radioactive power. So one of the most important thing in this calculation is, of course, this radioactive power. And these works studied the radioactive power of the R+ element after this neutron star merger. And this is famous heating rate. This is just heating rate. And this is R+ element heating rate. It's famous that this heating rate goes like T to the minus 1.3. And if you take just nickel and cobalt, this is just exponential, so constant and the exponential decline. So the heating rate of the supernovae and the macro kilonovae is very different. And this one is T to the minus 1.3. And this is sort of very simple power law, so, and famous, but it's not famous that why we should get T to the minus 1.3. So I want to discuss why we get this T to the minus 1.3 just from back of envelope calculation. So this is just some idea that what we should think about this heating rate. So this is just after the R process. This is proton number and neutron number, and these are the synthesized nuclei here. And these nuclei is so heavy and neutron rich, and all the material is radioactive, and then go to the stability line. This approaches the stability line, and each chain goes beta decay and approaches the stability line. So the important thing is these are beta decay, and there are many beta decay chains. So we can think this is something statistical assembly of these radioactive chains. So so this is very basic, but let me introduce what is beta decay. So beta decay is I have a neutron-rich nuclide and nucleus, then one of the neutron decays to proton. And this process, electron and neutrinos are radiated. And after this beta decay, usually what we have is excited nuclei. So then this nuclei decays, and then gamma rays emitted. So these electron and gamma rays can heat up the ejecta. So let's focus on this beta decay process, and then try to get T to the minus 1.3 argument. So because we have many decay chains, so in each chain, what we expect is d and dt. This is decay rate, goes like 1 over t. What this says is so we have a chain, and each time different species decays, and then in a logarithmic time interval, what we expect is sort of constant number of particles decay in each logarithmic time interval. This is sort of in a chain, the number of the particles conserves. Then the first guess is actually, okay, each decay, maybe we expect 1 MeV energy release, then the heating rate is just 1 over T. So this is actually the first guess of the Lee and Patinsky. They use 1 over T heating rate. This is based on the assumption that each decay energy is constant with time. But actually, it's a bit different. So the heating rate and decay energies depends on the time. And how it depends on the time? So we know the lifetime of the beta decay goes like e to the minus 5. So this is a sort of famous relation, but there is a reason. So 1 over tau is the decay probability. And basically, this decay probability is just proportional to the phase space volume of electron or neutrino. So we are thinking this process. So these two particles has a phase space. And this is 6th dimension in the momentum. And we have energy conservation and delta function here. And if the electron is relativistic, what we expect is just e to the 5. So 1 over tau goes e to the 5. And this we put this relation to this equation, and we get the heating rate is t to the minus 1.2. And also, we know the normalization of this heating rate. What is this? We have a basic fundamental energy scale, which is electron mass, MEC squared, and fundamental time scale, which is just written by the Fermi coupling constant and other Planck constant electron mass, and which gives you, this is a sort of time scale of the beta decay, which is 9,000 seconds, just written by physical constant. And we can normalize this heating rate by using these quantities, and then we get the 10 to the 10 at 1 day, erg per second per gram, and follow declines as t to the minus 1.2. So, but this is t to the minus 1.2, not t to the minus 1.3. So why t to the minus 1.3? Because here, so longer lifetime decay has a lower energy. So this approximation, that the relativistic approximation, is not correct. So in the end, the lifetime of the relativistic case is e to the minus 5, but non-relativistic case, phase space dependence is weaker. So then in its case, it's q equals like t to the minus 1.3. So this is just a phase space volume evolution from relativistic electron and non-relativistic electron. But lowest energy case, the Coulomb interaction is also important. It's t to the minus 1.33. And you can do a little bit more precise calculation, and what you get is electron heating rate is at early time it goes like 10 to the 10 erg per second 1 day, and it goes t to the minus 1.2. And late time, you have this, and then decline minus 1.33. And this is just comparison between this simple analytic form. And I want to emphasize this formula doesn't really have a free fitting parameters. So just these values are just calibrated by nuclear experimental data. So what we get is roughly consistent with the nuclear network calculation. So this is actually, this shows just this heating rate is quite robust as long as you have many beta decay chains, and not really depends on the detailed abundance pattern. So as long as you have many decay chains. So this is why we think this heating rate is quite robust for the output for macronovae. And another thing is gamma rays. So the Fermi's theory can't tell us the gamma ray emission, but we take the data from nuclear experiment. And this is the spectrum of the gamma rays. And most of the gamma rays are emitted around 1 MeV. And this is energy fraction as a function of time to each decay. So at a given time, for example, at 0.1 day, the half of the energy goes to the gamma rays. And like 20% it goes to electrons. And around at some 1 day or a few days, the gamma ray just escape because compton scattering is not so efficient. So heating rate dropped in this window. So now I want to compare this radioactive heating rate with this is just the radioactive heating rate that I showed, multiplied by some thermalization efficiency, and compare with the volumetric luminosity of this GW700817, take data from this Casoliva et al. So from basically all the way from half a day to 10 days, this R process beta decay heating rate is consistent with what we see. And another interesting fact is there is one Spitzer data point here. And of course, we don't know what is spectrum. We don't know how we can correct to volumetric luminosity. But just based on one band, we can calculate nu F nu. And actually, the luminosity is consistent with the R process heating rate up to 40 days after the merger. This is interesting enough for me. This event seems to be powered by R process decay. And there are many models that try to explain the details of light curve evolution spectrum. But let me introduce one of our model in this paper. So this is observed data from half a day to like 12 days, the volumetric luminosity and temperature evolution. And it's not easy to see, but there are 3 theoretical curves. Here is blue one. This is a classical macronova, which is velocity is less than 0.4 c. And with just this component, we can't really explain the early bright emission. So to explain this, we introduce some relativist component. So relativist macronova component, this is velocity larger than 0.4 c, which contribute mostly this initial first 1 day data point. And there's also cocoon component, but it's quite decline fast. So this one should contribute earlier than half a day, but we likely miss this emission. So basically, what we have is to explain the fast rise, we have to have this low opacity component, and maybe this relativistic boost help this to explain this early blue bright emission. But to keep this late emission and to keep 1000 Kelvin, we need some lanthanide rich component, maybe lanthanide fraction of 10 to the minus 2. Okay, so up to here is the macronova emission. And one caveat here is actually, if you have, so macronova heating rate is quite robust as long as you have many decay chains. But if the decay is dominated by just first big element, so light R process element, the heating rate is a bit different. So for example, this one is a gamma ray heating from the first peak element. So this is not looks like power law. This is just dominated by this decay chain. So you have a power law and dominated by this decay. So you have some exponential. So because this is completely powered by one of the first peak beta decay chain. So this is one caveat. If you change the opacity, maybe you want to change also the heating rate. So in summary, maybe the favored scenario is this one, because we need somewhat large mass, 0.05 solar mass, and also we want both lanthanoid and the heavy elements. So in this, specifically this event, probably this is so far favored scenario. So okay, I want to move on to this synchrotron flare next. So the synchrotron radiation is suggested as a gravitational wave counterpart at 2011 by Tsubi and Udi. And basically the process is just similar to GRB afterglow and supernova remnant. We have ejecta expanding with beta, and electrons are accelerated and the magnetic field is amplified in the shock. And these circumstances, you expect some synchrotron radiation. And the peak time scale is just the deceleration time of this ejecta, which can be written like this. And the peak flux depends on the energy and velocity of this ejecta, and also depends on the ISM density. And also synchrotron frequencies depends on the ISM density and then velocity. So it's quite strong dependence on this velocity here. So that it's very important to this radio or X-ray emission can tell us what is the velocity and energy in this ejector. So this is another way to study the ejected the outflow of the binary neutron stars. And because of this dependence, we can write this phase space, kinetic energy of the outflow, and full velocity of this outflow. So GRB has high Lorentz factor here, so it's faster rise, and this direction is bright. So more kinetic energy and faster ejector is bright and faster. So these are the important phase space. So GRB jet can contribute quite early light curve, and the dynamical ejector can be later and brighter. And this wind is too slow to contribute this synchrotron flare. And this is what we observed, and then Greg already talked about this. So this is S nu corrected by some spectral index factor, and this beautifully rise as a t to the 0.8. And this is a single power law. And now I want to explain a bit more about how we get this single power law rise. So as Greg mentioned yesterday, if I have a single velocity ejector in a constant ISM density, what we expect is rise as t to the 3. And at the deceleration time, it declines. So why t to the 3? Because, so let's assume equipartition. So the energy density of the electron and the energy density of the magnetic field is constant with time. Because this is constant density and the velocity is constant, then in equipartition, we have the constant energy density. Then the synchrotron flux from each electron is just constant, and the total flux is just proportional to the number of electrons in the shocked electrons. So that number of the electron just proportional to the volume of the shock, so that we get t to the 3 rise and then decline. So, but we can think different situation that we have different velocities to the different velocity gradient. So first constant velocity lies t to the 3, but slower and more energy one goes like t to the 3, but and peak brighter and later. So we have some summation of different shells. Maybe this is angular structure, maybe this is radial structure, and we can get some slower rise than t to the 3. And what actually the data actually says is the consistent with E greater than gamma beta is gamma beta to the -5. So it's a sort of steep velocity gradient. And of course, the Cocoon scenario has high Lorentz factor, and the dynamical ejector scenario has low energy. So the density, what we need is different. So Cocoon model, we need very low density, and dynamical ejector model, we need somewhat high density. So now I want to, so this paper, we just take as simple as possible, spherical and single power law, and with some maximum velocity, and then try to explain the data. Now I want to discuss is, so what is the physical origin of this in particular, this slower spherical component. So this is we expect some fast velocity tail from dynamical ejector. Although this bulk velocity of the ejector is moving like 0.2, 0.3 c, it's not so high, but there is some fast material moving 0.7 c. This is very small fraction in terms of the mass, but because when two neutrons are merged, there is strong shock around here, and some material is accelerated when the shock propagate the edge of the star. And we have something like moving 0.7 c. And this component is also important, not only the radio, but this neutron precursor, this fast tail can compose of free neutrons, and also this component is needed for cocoon shock breakout model. Maybe Tsubi will talk about later. So this is we looked at the recent numerical relativity calculation by Kyuchi et al. And this is a gamma beta energy greater than gamma beta. So you can see the gamma beta around 1. So this black straight line is just, we see this function here. So this is this function. And just we take one model that it's not so different from what we used in this paper. So just taking this energy distribution, we can calculate synchrotron radiation from this component. So this is a calculated light curve. So this is this dynamical ejector, and we just put by hand macronova main component, 0.05 solar mass moving 0.2 C. And these are the data, radio data. You can explain the radio data nicely. And this is HST data here. And this is X-rays. Basically, if the density is 0.01 per cubic centimeter, you can get consistent light curve with the observation. But the important fact is there is cooling break here in our calculation. The exact location depends on the structure of the outflow, but cooling break, we expect cooling break occurs around a few months. It shouldn't be too late. So we expect shortly cooling break will cross the X-ray band. And this density, I want to show one slide discussing about the density. So this is if you look at the X-rays from these nearby elliptical galaxies, and you can estimate you can get the diffuse X-ray luminosity, and you can estimate electron number density of these elliptical galaxies. And this is one of the work from this paper. And you can see at 2 kiloparsec, which is more or less this merger occurs. Around 2 kiloparsec, most of the elliptic galaxy actually has some high electron number density. So it's sort of this, what we get 10 to the minus 2 per cubic centimeter is somewhat consistent with this nearby elliptic galaxy density distribution. Okay, so finally I want to say a little bit about our process budget in the universe. So from this observation, we get the our process element production like 0.05 solar mass. And rate estimate, of course, it's only one event, but we can take this one as a then the rate is huge, like 2,000 per gigaparsec cubic per year. And still we have huge L bars. And then lanthanide mass fraction is about order 0.10 to the minus 2. And let me a little bit say something about this. So as I said, solar abundance, including from first peak, the lanthanide fraction is about 3% or 2%. So actually what we get, this is a bit lower than even the solar abundance. But if you look at the other metal poor stars, they supposed to affected by single R process production event. Sometimes you have a huge lanthanide fraction, but not much around the first peak. So in this kind of R process event, what we have is lanthanide mass fraction about 10%, which is much higher than the solar abundance. But sometimes we have this kind of stars that the lanthanide fraction is low, but the first peak around here, the abundance is high. So this kind of star, we have a lanthanide fraction much less than 1%. So we expect some variation in astrophysical observation as well. So maybe it's a good starting point that let's assume this lanthanide fraction, this event produced some solar abundance pattern from all the way from first peak to the third peak. Then we can calculate this kind of figure. This is event rate in Milky Way per mega year, per million years, as a function of the mass of the R process production in each event. So this is this green band shows that in order to explain all the R process element in our galaxy, you want to be around here. So if you have a very frequent event, you want small mass production per event, but for the low event, what you need is high production rate, high production mass. Produced mass should be high. And also there are different constraints. For example, this is dwarf galaxies. So this is just, if you look at the ultra-faint dwarfs, you have say 10 ultra faint dwarf galaxies, and each one contains like 10,000 stars, and only 1 or 2 ultra faint dwarfs show Arcos element. From this observation, we can say yes, 5 minutes. Our process event should occur around every million solar mass or 10,000, 100,000 star formation. After every 10,000 star formation, you have 1 Arcos event. So this is constraint from dwarfs. And also there is some interesting measurement of plutonium-244 in the deep sea and also the early solar system meteorites. So this constraint is here, and then this GW17 shows this around here. So of course it's just one event, and the error bar is huge, but it seems to be consistent to explain our process origins of the Milky Way. Okay, so let me click on. So there is also, because this galaxy is a S0 type galaxy, and based on the stellar population, the delay time of the merger is about maybe longer than 1 gigabyte. And also, we know some delay time from short GRB. So the short GRB seems to follow the cosmic star formation rate with some delay 1/t. And the minimum delay time is about 20 million years. And also we can say something delay time about the ultra faint dwarfs because they are very old, and star formation occurs just a small time window. So the delay time should be less than 1 gigayear to explain this ultra faint. And also plutonium measurements favor some decline of our process event this time. And how about the chemical evolution? This is a chemical evolution calculation and observation for this Milky Way stars. And this is alpha particle versus iron. So these are supposed to be produced by quark-collapse supernovae. And the denominator is just contribution of quark-collapse plus some type 1a. So once type 1a kicks in, then it's declined. So this is sort of what we understand so far. And this is our process element. This is our process element events. Roughly speaking, our process events divided by quark-collapse plus 1. Because 1a has some delay, and also our process events should have some delay. And what we get from simple calculation is something like this part. So late time decline is not really consistent with what data shows. So data says this steep decline. This decline is actually very similar to decline what we see in the alpha particles. So actually this nearby stars are around the high metallicity, not so high, but the metallicity larger, FeO by H larger than -1. It shows some decline. I think this is not so really consistent with the delay time picture of the Arcos event. Even this, we can say this diagram, we can say Arcos production seems to follow just star formation, not significant delay time. So this is one thing that possibly so this is someone. Thank you very much.
Well, thank you very much for an excellent talk that covered an enormous amount of material, and it's impressive how much of this work has been done over the last year and a half, I suppose. Let's ask if there are any. Well, there will be questions, I'm sure. So, yeah, George.
So I'll ask a question. So you were trying to explain all the R process, or almost all the R process in our galaxy,
Yes.
including our solar abundance,
Yes.
binary neutron stars. And you claim we need roughly 1 per million years, so we've had a few million, we've got thousand. The question I have is, when you look at, and I'm getting there to the number you need, which is, if you look at the neutron star merger radius in the galaxy, is it going to peak much strongly in the center and tail off significantly at the edge, unless these are propagating out of the galaxy? And then do you predict the chemical gradient across the galaxy? And then also, you can make an estimate of how many neutron star mergers you need in order to actually spread that material around the whole galaxy. Which is, they're only going to be sort of kiloparsec to 10 kiloparsec scale of materials you go throughout. So you have 10 to the fourth of those, and you got to get them there, in the first, 50 billion years. So is all that consistent?
Yes, about the gradient in a galaxy. So we don't really expect the neutron star merger occurs in the center, because more or less we expect to follow the stellar distribution, and also there is some delay and kick. It migrate probably outside. And in fact, I didn't mention about this. This merger specifically occurs around 2 kiloparsec away from this galactic center. But this is, if you compare with short Jerby offset, it's kind of very close. Short Jerby typically occurs around a little bit farther, typically around 5 or 10 kiloparsec. So I think to redistribute Arcus element in the whole galaxy is also a big problem. But I think one problem.
It also, what I'm claiming is it also tells you something about the minimum rate, which you must populate.
Oh, minimum rate from solar.
It tells you the total number that had to occur before in order to get stellar abundance, you had to have a large enough one, someone off near us.
Right.
Yes, we've got to make the solar abundance near the sun. Yeah.
Yeah, I wanted to work on that.
Yeah.
But the problem is the sun doesn't really migrate in the galaxy,
Right,
or
so the neutron
this
star
kind
had to
of
migrate there.
degeneracy exists. So it's not so easy to say.
I mean, offhand, when you were doing it, I was estimating you needed these 10,000 such mergers
Yeah.
just to get it reasonably distributed.
Right.
Yeah. So, look, okay, I've got a question. There you go.
Can you reiterate again on this the problem which you had with the abundance evolution of the galaxy?
Yes.
I mean, what was assumed in this theoretical model which you plotted on this?
Right. So this I didn't explain much. So let me explain. So our positive event, we assume delay time distribution was 1 over t, and minimal delay time taken to be 20 million years. And we vary type 1A minimal delay time. Type 1A also assumed to follow it 1 over t. And minimal delay time changes like different models, say we choose 40 million years. But in all the cases, what we get is because in the end, the rate of the R process and type 1A asymptotically the same gradient. And R process event divided by 1A event approaches some constant in this European mobile field. But actually, data shows this is quite steep decline.
Yeah, but I mean, you have probably assumed a homogeneous model,
Yeah,
right?
homogeneous.
I mean, I've seen galaxy evolution models with more sophisticated treatments of the locations and abundance injections,
Yes.
which reproduce this trend much better than your plot does.
I agree that such a sophisticated calculation can explain much better around here.
Yeah.
But the problem is the later time. The time scale is quite long, like 1 gigayear or more than 1 gigayear. At the late time, I think one zone calculation is not so different from sophisticated major galaxy simulation. And I also see this galaxy simulation also have this flattening around here if they take 1 over t those margins. So it's a sort of a common issue. It's simpler simulation.
I think probably better move on then at this. I think, okay, it's a very quick question.
I don't know if it is, but I'm not an expert. You've got this material coming out at very high velocity from this thing. Those velocities are very high compared with galactic escape velocity. So what's the fate of this material after a
Very
long
good
period
question.
of time?
Yes, it depends. So far we think this just interact with ISM and form a shock, and then this shock, this ISM stops this fast ejector, and in the end this slows down the escape, and then in the end the ejector velocity becomes less than the sound speed of the ISM, and this ejector will not escape from the galaxy.
And would the conditions wouldn't be right for any material to become neutral or to aggregate and to become like
Yeah.
particles
in
and
order
dust,
to get
and that
this
where
condition,
it will
you
be
need gas.
transparent?
You need ionized gas.
Yeah.
But it's possible that this may is ejected from some dust. Then this dust may escape just from this shock. In this case, the dust particle just escapes very high density from this object. But this is not so well studied.
Events in the halo and so on could have implications for cosmology and so on, and basically should pollute the intergalactic medium at early times. So I think it's an interesting issue. Along with, obviously, the other thing whilst we're setting up is the selection effects. We've obviously only seen one source, and it was unusually close and unusually bright, and there could be an awful lot of selection effects in there. And so, have you thought about how dependent this, how much this would change it with the population, say, from the next O3 and so on?
I personally expect it changes because the rate seems too high for me.
Yes.
And the rate is very high and the mass ejection is very high. And actually we get too much Arcos elements from this population stuff.
Yeah.
So I expect for next event we'll start to see
much more. It's a heroic amount of work that's been done so far, so it's a very good basis for moving forward. So let's thank Kenta again for a wonderful talk.